Have you ever pondered on the potential of harnessing the unfathomable energy of a supernova? A question that may seem straight out of a science fiction novel, yet it's rooted in the reality of our cosmos. A supernova, the explosive death of a star, is a spectacle of unimaginable power. For a brief moment, a single supernova can outshine an entire galaxy, churning out energy at a rate that dwarfs the output of our sun by billions upon billions times. This energy, in the form of light and other forms of radiation, traverses the cosmos, carrying the story of the star's spectacular end. Now, the thought of harnessing this energy might seem ludicrous. After all, the scale we're discussing here is beyond human comprehension. But isn't that the beauty of science, pondering the impossible, pushing the boundaries of our understanding, and imagining a future where the impossible becomes possible? Imagine the possibilities if we could tap into the power of a supernova. But first we need to understand what a supernova is. Think of a star as a cosmic pressure cooker. Over their lifespan, stars burn hydrogen, creating helium through nuclear fusion. This process releases a tremendous amount of energy, which pushes outward against the force of gravity trying to collapse the star. As long as there's enough hydrogen to fuel this fusion, the star maintains a delicate balance. However, when a star exhausts its hydrogen, things start to get interesting. It begins to burn helium, creating heavier elements like carbon and oxygen. This process continues, with the star producing heavier and heavier elements all the way up to iron. But there's a catch. Once a star starts making iron, it can't generate enough energy to resist gravity. The balance tips and the star collapses under its own weight in a fraction of a second. This triggers a shock wave that ripples through the star, causing it to explode in a brilliant burst of light and energy. This, dear listeners, is a supernova, a cosmic spectacle that can outshine an entire galaxy, if only for a short while. The aftermath of a supernova is equally dramatic. The explosion disperses the star's outer layers across space, creating a nebula, a vast glowing cloud of gas and dust. This material, enriched with the heavy elements forged in the star's core, will eventually form new stars and planets. But what about the star's core? Well, if it's massive enough, it'll collapse into a neutron star or a black hole. These are some of the most extreme objects in the universe, but that's a story for another day. So, a supernova is more than just a spectacular light show. It's the birthplace of the elements that make up our world, and a testament to the life and death of stars. Now that we have a basic understanding of supernovae, let's delve into their energy potential. A single supernova explosion releases energy that's beyond human comprehension. That's our starting point. To put it into perspective, let's embark on a journey through the cosmos and back to our humble home. Imagine, if you will, the detonation of a star. This isn't a quiet, gentle event. It's a cataclysmic explosion, a cosmic spectacle of epic proportions. In this single moment, the dying star releases about 1 octillion megajoules of energy. That's a 1 followed by 27 zeros, a number so large it's hard to even fathom. Now let's compare this to the energy production on Earth. Yearly, our entire planet generates roughly 200,000 terajoules of energy. If we convert this to megajoules, it's a 2 followed by only 15 zeros. This means a supernova releases about 1 trillion times more energy than Earth produces in an entire year. Isn't that mind-boggling? This immense energy doesn't just vanish into the void. It travels across the cosmos in the form of light and other particles, some of which reach our planet as cosmic rays. These particles, traveling at nearly the speed of light, carry with them the energy from their cosmic birthplace. Think of the universe as a grand cosmic orchestra, with each supernova playing its energy symphony. These symphonies of energy resonating through the cosmos hold a potential that's simply awe-inspiring. If we could capture even a fraction of this energy, it would be a game-changer. Yet, harnessing this energy is not as simple as placing a giant cosmic net. The energy from a supernova radiates in all directions, and the vast majority of it will never come anywhere near our tiny planet. But imagine if we could. Imagine the possibilities, the potential. Harnessing a fraction of this energy could revolutionize our world. The energy of a single supernova could power our civilization for countless millennia, transforming not just our energy infrastructure, but our entire understanding of what's possible. It's a tantalizing glimpse into a future not yet within our grasp, but one that's certainly worth reaching for. Theoretical physics opens up tantalizing possibilities of harnessing this energy. Imagine if we could tap into the raw, unfiltered power of a supernova. That's the dream, the aspiration of theoretical physics. And while we're still a long way from realizing this, let's take a moment to explore some of the concepts and technologies that might one day make it possible. First, there's the idea of advanced solar cells. Unlike the solar panels we have today, these would be engineered to withstand the extreme temperatures and radiation levels of a supernova. They would need to be capable of absorbing not just visible light, but all forms of electromagnetic radiation, from radio waves to gamma rays. This could potentially allow us to capture a significant portion of the energy released in a supernova. Then there's the concept of particle capture technologies. These would work by directly intercepting and containing the high-energy particles ejected by a supernova. It's a bit like catching a fastball thrown by a major league pitcher, but instead of a baseball, you're trying to catch a swarm of neutrinos moving at nearly the speed of light. Lastly, let's discuss the most exotic concept of all, the Dyson sphere. Named after physicist Freeman Dyson, it's essentially a megastructure that completely encompasses a star, capturing a large portion of its energy output. Now, imagine a Dyson sphere not just around a normal star, but around a supernova. The energy we could harvest would be astronomical, to say the least. Of course, all of these concepts come with their own set of challenges and limitations. The engineering feats required to build these devices are currently beyond our reach. And even if we could build them, there's the question of how to transport that energy back to Earth. While these concepts are purely theoretical at present, they give us a glimpse into a future of virtually unlimited energy. But the path to harnessing supernova energy is fraught with challenges and limitations. Let's delve a little deeper into these hurdles. First off, there's the sheer distance to consider. Supernovae occur in galaxies far, far away from our own. To put that into perspective, the closest recorded supernova to Earth was observed in the Large Magellanic Cloud, a neighboring galaxy about 168,000 light-years away. That's an astronomical distance, to say the least. Even if we could travel at the speed of light, it would take us 168,000 years to get there. So, the logistics of reaching a supernova, let alone harnessing its energy, are quite mind-boggling. Then there's the unpredictability of supernovae. These stellar explosions don't exactly run on a schedule. They are random and spontaneous events that can happen anytime, anywhere in the cosmos. Predicting exactly when and where the next supernova will occur is currently beyond our scientific capabilities. And even if we could predict them, we'd still have to deal with the fact that most supernova only last a few months at most. That's a pretty tight window to harvest energy. Finally, we come to the technological challenges. Capturing and storing the energy of a supernova is no mean feat. We're talking about an event that releases more energy than our sun will emit over its entire lifetime. That's an immense amount of power to contain and control. Our current technology is nowhere near advanced enough to handle such a task. And even if we somehow develop the necessary technology, there's still the question of how we'd transport that energy back to Earth. Despite these challenges, the idea of tapping into supernova energy remains a tantalizing prospect. The concept holds a certain allure, a testament to human curiosity and our ceaseless quest for knowledge and progress. As we continue to look up at the stars, we can't help but dream of the possibilities. The potential of supernova energy opens up new horizons for our energy future. Imagine a world where energy scarcity is a thing of the past, where our reliance on fossil fuels is replaced by the infinite power of the stars. This isn't just about keeping the lights on, it's about redefining our relationship with energy itself. Harnessing the power of supernovae could be a game-changer in our fight against climate change. The clean, limitless energy could drastically reduce our carbon emissions, slowing the warming of our planet and giving us a fighting chance to reverse the damage already done. But the implications go even further. The technological advancements required to capture and utilize supernova energy could propel humanity into a new era of scientific discovery and innovation. While the journey is long and fraught with challenges, the destination, a future powered by the stars, is well worth the effort.